Hello everyone and welcome to Differential Equations. The goal for today is simply to talk about what a differential equation is and then have a look at some typical real-world situations where differential equations tend to arise. So what is a differential equation? A differential equation is just an equation that contains a derivative. Outside of that, there's really no limitations on the format or the contents of a differential equation. One of the simplest differential equations might be something like the derivative of y with respect to x is equal to 3x plus 4. This is the kind of differential equation that you might have looked at in Calculus 2, for example. They would have said, here's the derivative of a function called y. What is the original function y? To answer that question, you might have integrated this. In vector calculus, you encountered partial derivatives. A differential equation can just as easily contain a partial derivative. So this would be another example. Something like f sub x is equal to 3 times x times y. This would be another perfectly good example of a differential equation. You can take the second derivative, for example, of a function called y, and then take 3x times y prime plus 4 times y, set that equal to e to the x. That's also on the table. And you're just as free to do strange stuff involving piecewise functions even. You may have something where you have y double prime plus 4y is equal to, say, 0 if your input value is greater than or equal to 0, is equal to 1 if x is less than 0. Any equation containing any derivative at all, whether it be a second derivative or a first derivative or a fourth derivative or a partial derivative, all of these things count. Now, solutions to differential equations are functions. For example, in the first differential equation listed here, a solution to this differential equation would be a function y, which makes this equation true. And using the techniques of Calculus 2, we can see that these solutions to dy dx equals 3x plus 4 are the functions y equals 3 over 2 x squared plus 4x plus some unknown arbitrary constant c. This function makes the differential equation true. If you take the derivative of y with respect to x, then the result will be 3x plus 4. So when we're solving a differential equation, we're trying to find a function which makes the differential equation true. Now, differential equations arise all the time in real-world scenarios. The only requirement is that the equation contains a derivative, and therefore differential equations are appropriate in any situation where you have a quantity that's changing, because changing quantities related to rates of change are related to derivatives. One example of a situation that can be represented by a differential equation is that of short-term population growth. Suppose you have a population and you're measuring the size of a population by a function y whose input variable is given by t. In the short term, you can think of the rate of change of population as being proportional to the population itself. When the population is small, when the value of y is small, then there are not many members of that population who are giving birth to new offspring. That causes the rate of change of the population to be rather small as well. But when the population is large and y has a big value, then there are many members of the population who are capable of reproducing and producing offspring, and that causes the rate of change of the population to be larger. The population increases faster. Now, if you're watching a population and measuring its size over a long period of time, this model, this differential equation, begins to become less appropriate. Because in the long term, population growth, the rate of change of population size, is dependent not only on the number of members of your population, but also in some sense in the amount of space that your environment has left. In a real-world situation, an environment can only support a finite number of people or of creatures. After a certain point, you either run out of space or food or other resources. The number of members of a population that an environment can support is called its carrying capacity. And one of the things that's been observed about most populations is that as they get closer and closer to the carrying capacity, the population begins to grow more and more slowly. So in long-term population growth, when populations start to get close to carrying capacity, that situation is better represented by what's called the logistic differential equation, which says that the rate of population change is dependent not only on your existing population, but how close that population is to carrying capacity. And that closeness to carrying capacity is represented by this second factor, 1 minus y divided by k. I know a lot of folks have qualms with Wikipedia, but it can be a nice way to introduce yourself to a brand new subject. And Wikipedia is surprisingly reliable for mathematical things. For example, here, they also are giving us the logistic differential equation for long-term growth of a population, where they're using p to represent the population after time t. They have the growth rate r, and then they are also using k to represent the carrying capacity, the maximum population size that an environment can sustain. Newton's law of heating and cooling is another situation where differential equations are involved. Newton's law of heating and cooling has to do with the rate at which the temperature of an object changes. So it has to do with the rate of change of, maybe I'll call it capital T for temperature, with respect to lowercase t for time. Newton's law of heating and cooling says that the rate of change of temperature is proportional, so let me just call it R times, is proportional to the difference between the object's temperature and the temperature of its surroundings, which is sometimes called T sub ENV, or the temperature of the environment. So here's another differential equation. The rate of change of temperature is equal to R times the current temperature minus the temperature of the environment. Differential equations famously and frequently arise in electromagnetism, in particular in Maxwell's equations. For example, here we have an electric field, which is being represented by the letter E, and we have a magnetic field, which is being represented by the letter B. Both of these are vector fields, and the vector is dependent on the position at which you are measuring the electric field and at a given time. The same thing is true for the magnetic field. This equation in the purple box says that if you take the curl of the electric field, then that's going to be equal to the negative of the partial derivative of the magnetic field with respect to time. So the curl of the electric field is related to how the magnetic field is changing over time. Differential equations often arise in fluid flow analyses and in fluid dynamics. This entire page on fluid dynamics is absolutely chock full of differential equations, but we can see a few right here. If I take the derivative with respect to time of the total mass of a fluid inside of a volume called V, then that's going to be the same thing as the negative of the integral over the surface of that volume of the fluid density times the flow velocity vector. So basically what this is saying is that if you are looking at the mass of fluid in a certain space, and the mass of fluid in that space is changing, it has to change as a result of fluid coming into or leaving that volume, leaving that space through the boundary of that space. Mass cannot just spontaneously appear or disappear from inside the volume. It has to pass through the boundary. Spring mass systems can also be represented by differential equations. So suppose we have some spring to which a mass is attached or perhaps suspended. Now, independent of any external force, the spring mass system is going to be in a state called equilibrium, basically a resting state. But if we come in and we push/compress the spring, or if we extend it, then the spring mass system gets disturbed from equilibrium and the mass moves its position from equilibrium. So we introduce a variable called x usually. X is a function of t, which measures the object's position relative to equilibrium at time t. Now suppose that I come in and I exert a force on the spring mass system in order to elongate it. And I'm going to change the position of the object suspended from this spring from 0 at rest at equilibrium to a new position called x. As soon as I do that, a force begins to act to try and return the spring mass system to equilibrium. Now, we know from Newton's laws that the force acting on an object is equal to the object's mass times the associated acceleration of the object. And we know that acceleration is equal to the second derivative of the object's position. So in this spring mass system, the force acting on the object, which is equal to the mass times the associated acceleration of the object, is proportional to the position to which I displaced the object. And there are reasons for this negative omega squared that I'm not going to go into now, but this is really just to make sure that the force is moving in the opposite direction as the movement of the object away from equilibrium. If you move it down, the force will act upward. If you compress the spring and move the mass upward, then the force will act downward to bring it back to rest. So this would be the differential equation that is associated with a simple spring mass system. Predator-prey systems. Predator-prey systems can also be represented by differential equations. And this is a pretty unique representation because predator-prey systems involve what's called a system of differential equations. You have two interacting populations in this example. You have a population which is representing the prey, for example, rabbits, and you have another population which is representing the number of predators, for example, the foxes. And you're looking at how both of these populations are changing simultaneously, dx dt and dy dt. Now, the rabbits are basically self-sustaining. They can eat grass and eat plant life or whatever, and so over time, left alone, their population will grow proportional to the number of rabbits that you already have. The more rabbits, the more rabbit babies, so the population grows faster. However, the rate of change of rabbit population is also affected by the number of predators, here called y. The more predators there are, And the more rabbits there are, the more likely it is for predators and rabbits to interact. The easier it is for a predator to find and eat a rabbit. So dx dt is also affected by x times y, which represent the amount of interaction between prey and predator. Likewise, dy dt is affected by the amount of interaction between prey and predator. The more prey is available for predators to eat, the better off they are, and generally speaking, the more predator babies, fox babies, are spawned. But as there more and more foxes appear, there's more competition for the same resources, and so there's also this term minus constant times y, which says that as the number of predators grows too high, that actually will hinder the survival of the species because there's too much competition over the limited number of resources. So finally, let's look at one more fairly famous example of a differential equation, which is the mixing of two chemical solutions. So you have some sort of mixing tank. And let's suppose that salt water is going in, as well as pure water, which is also going into the tank. The salt water and the pure water mix in the tank, and then the mixture gets drained out. If I look at the rate of change of salt in the tank over time, then that is going to be represented by a differential equation that we're going to set up and study ourselves a couple of sections from now. And we're going to use that actually, we're going to solve that differential equation to find out exactly how much salt is in the tank at any given time, depending on the concentration of salt water, depending on the rate of flow of these two solutions into the tank, and depending on the flow rate of the mixture out of the tank. Now, differential equations arise frequently in all aspects of life, and in particular all aspects of STEM. But the tragic thing about differential equations is that it is very often very difficult to actually solve them. What has happened historically is that someone has run across a real-life situation containing a differential equation, for example, maybe one of Maxwell's equations, and then they sat down and they tried to figure out how to solve that differential equation. Then, if lucky, the solution method for that specific differential equation could be generalized to solve maybe a couple of other similar-looking differential equations. And even today, we follow a very similar process in our class. We introduce a type of differential equation. Generally speaking, a type of differential equation that is similar to a famous differential equation that came up and needed to be solved for some practical application. And then we're going to study how to solve that type of diffie-Q. And then we're going to use that technique in as many different applications as possible. So that concludes today's video. We talked about what a differential equation was, looked at a couple of different abstract examples of differential equations, then took to the internet and looked at a few examples of differential equations that arise in different fields and applications.